Xavier, you on the line? Okay, sounds good. So what we're going through today is to introduce deep learning and the terminology, and then we quickly will jump on to the cAInvas notebook that we would go through at a high level as to how did we develop that prototype. And it's just a proof of concept. It's a POC that somebody can take and build a company around. And so we will go around the technology and talk about as to how one can go doing about that shortly. But before that, we should go through some of the deep learning concepts. And this is what I'm going to cover next. So deep learning networks, and the introduction starts with networks. So what are networks? Anything that is connected in an arbitrary fashion with a certain order with an intention to exchange information is essentially a network. And we are aware of quite a few around us. We all use Facebook. That's a social network. LinkedIn is a professional network. And then we have telephone lines, which are switched telephone networks, communication networks. We have electricity coming to our house. So it's a circuit network. And of course, our computers are connected through our home router, Wi-Fi, and the internet. And all those are networks, right? And then you have railway network, road network, airport networks, and stuff, right? So anything that is connected with an intention to exchange information, and it's ordered arbitrarily, and that's called a network. And deep learning network is one such network. And the name neural network comes from the neurons, which is kind of funny because I don't believe it is similar the way the information flows. In a human brain, there are typically 80 to 100 billion dollar, 80 to 100 billion neurons that are connected, and they are connected pretty densely. And what that means is there is no layer, there is no ordering, and as opposed to the artificial neural network that are connected pretty sparse. And there is an information flow that is ordered from forward to backward and in the loop, or backward to forward, depending on the situation. But the flow of the information in artificial neural network is fairly controlled, unlike a human brain. So when an entity in the network is represented as neurons, it's a neural network. And a neuron is kind of a fancy term for something W times X plus B. So W is a weight, it's called parameter, it's called a learning parameter or model parameter. And bias is also part of that. So if somebody's referring to where are my model parameters, what they're asking is, where are my weights and biases that this network is trained on. So and the W times X plus B is essentially a universal function. And it can be shown that with the simple W times X plus B, which is essentially general element matrix multiplier, and with the help of an activation function, it can approximate any function, any arbitrary function, and that's all you need. So W times X plus B followed by an activation function is essentially can give you any function, however complex, however arbitrary it is. And so it's a good choice for W times X plus B, and convince yourself with connecting few neurons one after the other and see what kind of functions do you get. Now we'll talk about that in a minute. So what is deep learning? Essentially, let me talk about the one layer, an oversimplified version of a layer. So we create hypothesis using a network, and we say this function, the input that we have, we can train our neural network of 3 layers with X number of inputs and Y number of outputs with these many neurons in every layer and connected together in a form called network. And once you specify that using Python or C++ or whatever have you, then optimization algorithm will run on it, and then will start changing these W's and B's. And that's where your learning is happening. That's where neural network is being trained. And the optimization that we use is non-trivial in the sense that it computes error gradients to find the next weights and biases. But to not delve into the complexity, what you see on the slide is in the input, which is x1, x2, x3, going to another neuron via a branch called W1, W2, and W3. And what this arrow means is essentially a multiplication. So x1 is being multiplied by W1. So if you ignore x2 and x3 for the time being, A1 is nothing but x1 plus W1. W1 times x1 plus B1. So this is the bias for this neuron. So this is as simple as that A is equal to W times X plus B. Now, if you consider x2 and x3 along with W2 and W3, what it becomes is a matrix and vectors. So x1, x2, x3 is one vector, W1, W2, W3 is another vector, and A is equal to still W times X plus B. Here, W is transposed. So it's not, you can't multiply two vectors without following certain rule. So to follow and obey that matrix multiplication rule, you need to transpose W before you can multiply that to X. So W transpose times X plus B. Now that detail is omitted here, so I'm not going to get into putting transpose every time. When I say W times X, you need to make sure the dimensions of a vector or a matrix or a tensor is properly aligned. So the whole idea of giving this introduction is it's fairly simple in its atomic form, but when you start putting layers after layers, it becomes beast and non-trivial to even look and try to understand it. And when I'm talking about the complexity of it, I'm talking about 40,000 input neurons, and anywhere from 15 to 150 layers, one after the other, and approximately anywhere from 1 million to several million parameters, and that becomes very difficult for any basic linear algebraic system to optimize that too. So we needed a new framework for deep learning alone, and that's where the LXNet started the revolution of deep learning with the demand by asking the hardware community that we need different kind of algorithms, different kind of hardware, different kind of software. And so 8 years after, we practically have very specialized pieces of hardware and software for all kind of applications. So deep learning terminology, and I'll go through one at a time. So neurons we've already covered. Weights and biases are essentially parameters of your neurons. Like I said, activation is equal to W times X plus B. Your W and B's are learning parameters. And model parameters it actually includes more than weights and biases. In some cases, you would need more information. For example, if you have a convolution layer, you might need to know what kind of filter, what kind of dilation, and what kind of groups do you have. So each of these operators and layers would need more information, and those are collected in something called model parameters. And perceptron is another name of a simplified network. Compute graph, essentially the way you compute the information. So you have some information packed in the form of a tensor or a matrix or a vector that you need to take through and compute. So it could be as simple as addition and multiplication, right? Like I said in the last slide, you have W, you have X, which is an input, and B, which is a bias. You want to multiply W to X and add B to that. Now you need a multiplier and an adder. So if you see the compute flow, essentially will take W and X first, that goes to a multiplier, and then the result of multiplier goes to an adder, which takes a bias on top and adds that. So it's kind of a compute graph, which is directional. The flow is happening from input to output, and that's as simple as that. Layers or operators, anything that constitutes how these operation must be performed. Like I said, general multiplier, your sigmoid, your sine, cosine, tan functions. There are several ways of creating your network. And all of those are valid ones. Those are called operators. And typically, the difference you would see between normal operators like plus, minus, multiplier, division, modulus, and so on, that are part of every high-level language. The difference here is you have very high number of operators in deep learning, in excess of 200, which are very popular today, as opposed to 5 or 10 operators in a normal language. So that's the difference, and that's the reason that we need a specialized hardware and a software stack to be able to deal with that. Activation functions are something that makes a network non-linear and being able to learn much faster, and makes the whole thing as a universal approximation, approximator of any kind of function. Forward propagation refers to the information flowing from input to output. Input to output is generally considered a forward direction. So in that, whatever is flowing in terms of compute, parameters, error gradients, is called propagation. And if it's going from input to output, it's forward. If it's going from output to input, it's backward. Now, why do we need backward propagation? Is essentially we need to propagate the error gradients that we computed the output and take them through the graph backwards. And once you have the backward gradient, that is used to compute the next step as to that's how the learning would occur. You need backward propagation to find backward error gradients on each one of these neurons for you to be able to find the next weight. And this loop, this optimization loop goes for 100, 200, 500 epochs before you have your network accuracy to a desirable point. And so the error gradient is nothing but in the first loop, you get the error, your output is X, you predicted X1, so X minus X1 is your error, and the gradient is what step did you take. So it's a slope that you computed the output, and there is a backpropagation algorithm that takes that error gradient and distributes through the rest of the network. Like which error gradient is, which neuron is contributing by how much to this final error gradient. And after this distribution, what you can do is you can use each one of those localized error gradients to find the next W. So W next is equal to W plus minus your slope, which is error gradient, times the last weight. So, and this is essentially your propagation algorithm, which we covered in the last lecture. Stochastic gradient descent or ADAM optimizers, they all do essentially the same thing to find the next W using this error gradient. So error gradient is required. Now, vanishing and exploding gradients is essentially referring to where your gradients, when you're propagating backwards, it essentially starts to become zero. When it reaches that level of very low number, very small number, then your learning, meaning your next W, would be very similar to your last W. What that means is your learning has become painfully slow. So instead of 100 epochs, you might take 10,000 epochs, and that's a long time. And it's a problem in training the networks, which will take a long time and large amount of memory and energy and power and compute. So these algorithms, they do take care of that. They recognize, for example, ADAM optimizer is very good at identifying when the gradients are going close to zero or exploding, for that matter. So if the gradient is very high, then it starts to multiply, and it can go out of the computer's range. For example, a normal 32-bit integer can only hold 4 billion different values. And if it goes more than 4 billion, which is quite likely given the number of parameters we have, then it just becomes not a number or infinity in the regular mathematics terminology. And at that point, you can't compute anything. So not a theoretical problem per se for mathematicians, but for hardware engineers, it's practically a theoretical problem where they would like to keep these numbers to a reasonable range where they don't explode. So this is all about deep learning terminology that you would hear in the textbooks and stuff. Now let me spend some time on this graph. Why is deep learning getting more popular, right? This is a fairly popular graph that has been touted many times in the academic papers, media, and such. And what this shows is if you increase the amount of data to some of these algorithms, for example, traditional learning algorithm, it will start to learn fairly quickly, and then it will improve its performance. And by performance, I mean the accuracy mostly here. And so it will improve the accuracy and start to become flat after some point. And the higher, it doesn't matter if you feed more data after a point to these traditional learning algorithms, the accuracy just stays flat. So if you use small neural networks instead of traditional algorithm, then the accuracy starts to become higher, and again it starts to flatten out after certain point. At that point, you might want to increase the number of layers and neurons in your neural network, and it'll start to learn with better accuracy. And larger networks would give you more accuracy. So the point here is that with the amount of data, increasing amount of data, and increasing the depth and the size of a neural network, your accuracy will continue to go up and will hit close to 100%. So that's the idea. And why is that exciting? Why is this this exciting? Is because back in 2000, we didn't have many images. 90s, when the internet bubble started, there were not many images because the speed of the internet was in kilobytes. So the most popular back in 96 was these modems, which were running on 56 kilobytes of bandwidth, and that is very small for an image. So most people relied on the text. And as and when the speed started increasing, we moved to images from 2000 to 2010 roughly, and then moved to videos and started improving resolutions and so on. So the point is, we are gathering as a human species, we are gathering large amount of data that we have, and there is a lot of intelligence in the data that we can use to find nuggets to help us, our society, become more productive and in ways more than one. So, and this data is not going to stop today or tomorrow, right? The more data you have, the more things you can find that would surprise you. So deep learning has a promise that with the high amount of data, your performance will go up. And that is exciting. So it's not a promise of today, it's a promise of tomorrow. And that's why deep learning has gained more popularity compared to rest of the machine learning algorithms. So this slide talks about types and applications, neural network types, feed-forward, recurrent neural networks, self-organizing neural networks, and these are some of, so self-organizing is for part of unsupervised learning, feed-forward, recurrent are part of supervised, and you have applications. You can do prediction, classification, you can do clustering, you can do optimization using neural networks. And I want you guys to look at this video. Let's hope that you guys get the sound, but it's not about sound. It's basically judging your ability to find how good is your vision system is. And I would play it once, and I would give you 5 to 10 seconds to find the differences you have seen from the beginning to the end in this. And this was conducted by MIT. It's an experiment that's conducted by MIT that humans are focused in finding changes in the scenery, and that's how the human vision system in the brain works. But then you can trick it fairly easily. So what I'm going to challenge you is notice the scenery here and try and find how many things are changing. And I promise you, you would find way more than your brain can spot. So let's go. It's a 15-second clip, and again, the challenge is you need to make note of things that will change in this scenery. There you go. Okay, so it basically stopped, and I don't know how many of you noticed, but what this scenery is trying to do is to make you focus on this white car, and everything else in the background is changing. And I can go on and tell you, because I've seen this clip multiple times, this entire building right here on the back changed. The colors of these doors changed. This entire balcony changed. And there was a pedestrian right here that changed. The logo showed up, and there were a number of things. So what I'm going to do is I'm going to start in the beginning so that you can see this person walking here, the color of the building as gray, and this is the green outlet and the door color and the balcony and everything, right? So let's look at that. Let me go to the end so that you can spot the change now. Do you spot the change? So the pedestrian is gone. This whole building changed. A number of other things happened. So this was the door was so the door color changed from reddish to greenish. Nobody noticed that. There was a person walking in front, and this whole shop changed from a bakery to something else. The signboard showed up, the chairs disappeared. So there were a number of things that actually changed slowly in front of your eyes without you noticing. And that's a trick that human vision system plays, that you're not looking for things. It's not able to identify many things. And that's where deep vision is outsmarts human vision system. So with that, the idea here is not to sort of show that deep learning is better than humans. It's not. But then these are computers, right? Somebody said like over 50 years ago, computers are stupid, but they are very, very fast. Meaning you train them what you are supposed to train them on, and they will do that thing 1,000 times faster than you. But they will continue to do the same thing. And that has a wisdom in it, meaning they would not do something different like humans would. First time, you would do one thing. Second time, you won't repeat exactly the same thing. You would do something different without you noticing. And you can call it learning, you can call it mistakes, whatever it is, but it's not repeatable. Human behavior is not repeatable at an atomic level. And computers are perfect for that. And they're very fast. And that's the idea here. Deep learning can spot something that human vision will completely miss. So back to our linear feed-forward neural network, right? This is an oversimplified version of a neural network with very simple, 6 neurons. The idea here is for you to draw and understand the mathematics behind it if you are so keen. Not required, so I'm not going to cover it. But the idea is that you have input x1, x2, x3 that is going through 2 activation functions, 2 neurons, 1 layer with 2 biases, B1 and B2, and then finally goes to the last layer, which is an output. And how these x1, x2, and x3 are flowing through the y, if you do the math, for example, A1 is W11 x1, W12 x2, addition of that, and then followed by addition of B1 is part of these 2 neurons. So if you follow the neurons and the weights, and then you do the math and add an activation function in these 2 layers, you will find just these 6 neurons can overwhelm you. Will take you over close to 20 minutes. But it's a good part of understanding as to how the information flows into these feed-forward neural networks like CNNs. And this is your example of what happened in the last slide. If you were to do math, this is what you get away with. So this is a solution to the last slide. With that, I would like to take you to a beautiful site that Google maintains as part of their TensorFlow initiative. And this helps you understand what neural networks do in general. And this lets you add more layers, more neurons, still keep it simple, and it'll give you the function that the neural network is supposed to approximate, right, with these. And this is a simple, general element matrix multiplier with an activation function. So you can change the activation. I'm going to use ReLU. No regularization. You don't have to know regularization or regularization rate. You can leave that for now. Keep the learning rate to 0.03 optimal. And I want you guys, I'm going to run a couple of experiments just to show you. And what I'm going to do is I'm going to keep this x1 and x2 only. There are no other features that I'm going to add. And let me add that first. And I'm going to take this. This is reasonably complex function. What this is essentially a data set of 2 different points, and we want to classify. We want to train this network to find if the given point is blue or yellow, right? And so I've created this network just by pushing a few buttons. And what I'm going to do is I'm going to train, and these are epochs. Epochs are essentially iterations in a larger sense that when the number of samples, for example, it might have number of samples equal to, it should be somewhere here. Okay, it's not. So let's say 200, 100 blue and 100 green, 100 yellow. And when these 200 samples are done propagating through the network once, it's called 1 epoch. So I'm going to run it to, let's say, 200 epochs and see what kind of function does it come up with the boundary to classify blue versus yellow. So here you go. So you see the circle it has created, and the boundary is shown with the white aura, and that's a perfect classification boundary for you to sort of take this neural network and ask it to find, given this yellow dot, is it yellow or blue, and it'll tell you that this is yellow, right? So it's fairly easy for this complex network. So, and what I'm going to do, I'm going to keep everything same. I'm going to reduce the number of neurons, and actually I'm going to reduce the layers, so it becomes more complex. more difficult to find for it to. And now what you will see is with this smaller network, it's going to struggle to come with that boundary. Boundary won't be, it can't find circular boundary, and there is a reason, mathematical reason behind that, and that can be derived from the network. But I just want to look at the animation, which is beautiful. That will add to your understanding. So look at this blue and yellow. It's trying hard. And right now, it's not able to form that boundary that will, so it has done over 200 epochs compared to 14 epochs in the last round. It still has a large error, meaning if you give this yellow point and ask this neural network whether this is blue or yellow, it'll say this is blue, which is wrong. And the difficulty seems to come from the simplicity of the network, is my point. So you can actually derive quite a few points and enhance your understanding as to how these neural networks work using that website to start with. And the experience will tell you when you're developing your own neural network, do you want to add more neurons, more layers, and what would that do? And once you have that sort of intuition, then you can start, throw your curiosity on the mathematics side as to why this was not able to create the circular boundary that was needed. And you can do that for 1, 2, 3, 4 types or in smaller samples of data sets. But when your number of samples go in thousands or millions, and with features ranging from 10,000 to 100,000, human brain does not have enough power to understand and wrap the head around, and that's why we need some of these tools. So I'm going to stop here. There is a lot more to it, and we would continue to discuss as and when time comes. But I want to sort of give you a little bit of excitement as to how did we go and develop a prototype for ASL model, which is American Sign Language. So what this is it has an IMU unit, which you can't see. This is a board from Arduino Nano 33 IoT BLE Sense. And this is approximately $20 or $25. Has a processor about 60 megahertz running at probably 50 or 60 megahertz, and has a memory of about 256 kilobytes. I say kilobytes. And these are microcontrollers. They don't have hard disk or other ports. These are very simple pieces of hardware that can still do the job. And this is where we are focusing our efforts on. We're bringing these networks and the magic of AI to these tiny devices, and that you can create the product and create a company or sell it to a larger marketplace, or just do it for your hobby, or just to show off, to your family members, to your moms, to your dads, and your girlfriends, to impress them as to how smart you are. And we are planning to simplify this whole thing, one day at a time. This notebook is, I'm going to take you step by step as to how this was done. Part of that is data. How did we capture the data? And I'm going to cover that in the next lecture as to how did we use this board, what kind of program did we put in to get the gyroscope data out of this board and created something like this. So this is the AX, AY, and AZ. This is acceleration as to when you move. When you say high is like this. So you actually do this, whatever this is. Your hand and the fingers are moving in different directions, right? So we are capturing exactly that as to what kind of acceleration this board would have, or this IMU when it sits on your fingertip in a glove. What kind of acceleration would this have? So this sitting on the tip of your finger would give you how fast the finger is moving, and that's the gesture the mute person is making. right? And so that's one part is acceleration. The other part is gyroscope, which is essentially your X, Y, and Z coordinates, right? At every point. And this tiny thing can collect over 114 samples per second. And that's very granular compared to what a human vision can see, which is anywhere from 15 to 30 or 40 frames per second. This can collect over 115. And if you add more powerful board, you can go up to 1,000, but it's not needed for the simple POC. And the whole idea is not to rely on acceleration, just use GX, GY, and ZZ. And how we collect that data, I will go through the program and the entire setup in the next lecture. But for now, let's focus on this notebook. So what we have is we are given this hi and what's up kind of gestures. And we are going to do develop a neural network that identifies the sign, what sign was made when the fingers moved in certain way. And so this is based on 2 signs. You can increase that to 1,000 signs, and that's practically 95 to 98% of the sign language vocabulary, for every kind of sign language. So every region has a different language. Americans have sign language called ASL, which is American Sign Language. Indians and South Asian regions, they have slightly different version of that. And just like languages, right? They evolve. So sign languages also evolve, and they have different signs in different parts of the world. So what you do is you essentially start with uploading the data, which is 2 CSV files. And I already showed you what hi.csv looks like. And these are a bunch of samples, which are over 6,000. With the 6 features. We're going to use last 3 GX, GY, and ZZ gyroscope features for this proof of concept. So we already uploaded the data, so it's right here. This part is checking whether do we have the data. And then we are going to sort of see if there is a regularity in this data. So this is practically optional. You don't have to do that if there is somebody who's given you data which is clean. But we are going to plot it and see if this is what kind of data are we getting into and what kind of neural network should be designed, right? Now, given the gyroscope data, which is this, your X, Y, and Z coordinates, how they move. This is one for sub gesture, and this is for high gesture. So all we need to identify is whether this is high, sub, or something else, right? We're not going to use accelerometer. We're going to use only gyroscope. So we are preparing the data here. We looked at the data. This was our data analysis. Nothing needed. It's already clean. And we are preparing the data for further ingestion by the neural network. So this is just, going through every sample and randomizing it, essentially. Samples per gesture. We have created a window of 119. So we are doing per second basis. The assumption here is the mute person is making 1 gesture per second. And that might vary. And you can create a parameterized approach to create the network in that case. So you take those many samples, 119 samples, and then combine them together and feed it to a neural network and ask the neural network, was it a high, was it a what's up, or was it something else? And it'll give you an answer. So this is doing essentially taking all those features and putting them into data frames. And there in the next cell, we are randomizing and splitting the input and output pairs for the training. So this is train and test split that we have not talked about yet. We will talk about how to split your data sets and why is it needed and things like that in the next lecture. But this is ahead of that. Now we are randomizing, like I said, we are randomizing the inputs, and randomization is very important. I'll talk about that in a minute. And splitting the data into train and test. And we are only going to show the training data to our network. Test, we will validate how good is the model. And this is our ASL model. This is built in PyTorch. In case you guys didn't notice so far, this is all PyTorch code in Python, written in Python. So this is where the heavyweight lifting comes in. So I've created two models, one with 3 layers, the other one with simpler layers. So this is for the Arduino fit. Looked at some of the parameters in the Arduino board we have. If you change your board, you might want to change some of this so that it fits in the memory of your network. And then you create this model. Optimizer, that, like I said, we discussed, this is a stochastic gradient descent optimizer that is going to look at this model and give us and train our network with the parameters. And the criteria we're going to choose is, for loss, is cross entropy loss. We are going to talk about cross entropy in the next lecture too. For now, just look at and enjoy what we can do with the knowledge that we will gather in the next few lectures. So this is how you would train the model. This is typical, no magic here. It's a simple PyTorch code. You go about, train the neural network. And so this is your output. Now you see the loss is essentially your accuracy for classification. And it starts to come down as number of epochs go high, and you see accuracy will start to improve. 50% accuracy for a binary neural for a classification network with 2 classes is practically useless. So it starts with that useless state. Either this is high or sub. And if it is 50%, it's essentially taking a random guess. So at this point, it's going all random. And then in the 7th epoch, it starts to improve. Quickly jumps to 65. And then in few epochs, you will see the accuracy go up pretty high. In 20 epochs, we are sitting on 92%. You can stop if you like, if 92% is good enough for you. If not, for somebody like me who would like to push things to what they can achieve, I do that with people too. So this is where 100% is. Now you see, just like humans, you catch up on nuances of the problem and patterns pretty quickly. In 20 epochs, you have accuracy down to 92%. But if you want to be a perfect, like #1 person on this planet, you got to go and do 150 epochs. And there is a almost 10x effort that is needed. And that's the difference between a champion and a regular person. They would stop at 20, and a champion would like to find more and would get excel over the time, over the months and years. This is what is needed. So you give more time, you learn more, is kind of what is shown here. Now we have our network trained. We would like to evaluate as to how this is performing on the data. We did not show it. And again, we are glad with the accuracy there as well. And rest of it is, how do you bring this model to the board that I talked about. That rest of this is just the code that you use our platform and flash this device to bring this model onto the Tiny board. So the first step is you save that model as an Onyx model. And then you sort of install and compile the ML model for Cortex-M4. So this particular Arduino board has Cortex-M4 processor. And so we have a command called deepcc, which lets you compile. And it'll also give you C++ file if you are so keen to develop the application further. And that's the key of bringing a Python network to a smaller device like this. Even though it's very simple, I mean, it's a simplified step. There won't be much effort needed from your side, and that was the idea. That we should be able to bring these networks to smaller, tiny devices. So we created a compiler that helps you. If you are so keen to get into the C++ side and would like to, develop that further, we have a C++ kernel that lets you experiment and compile the networks. This is slightly more involved, but if you know C++, this should be easy enough for you. So there is a utility that we have embedded on our platform, CPP to IPYNV. We can simply import this and convert the CPP file that our compiler generated as an intermediate step to a notebook, and you can continue developing the rest of this. So right now it's just a network, but let's say you were to develop something more flashy thing, right? For example, you have the output that this was high, now you want to translate that output to a spoken word, right? You need a speaker, and you can connect your phone, for example. That can be a speaker. You connect your phone to this board which has a Bluetooth, and so you can pair your phone to the Bluetooth and send the words to your phone, and phone would say hi or what's up and other things. So you keep your phone handy, that in your back pocket or front pocket. That becomes your speaker. If you don't have the speaker in the back of your hand as a glove speaker, then you can do a number of things based on your ambition and desire to bring this proof of concept to the next level. So with that, I would end the lecture here. It's almost an hour, and would open the floor for further questioning. Xavier, it's a good time to stop